Hi everybody, welcome back. In this video, I will give an introduction to colligative properties. I'll show you a video that gives you some nice visuals. In addition, I will dive into vapor pressure lowering. In future videos, I will discuss freezing point depression, boiling point elevation, and osmotic pressure in more detail. All right, so let's go ahead and get started.
Hello and welcome back. In this video, we'll look at a set of properties of solutions known as colligative properties. Colligative properties depend on the number of particles dissolved in solution, not on the type of particle. An example of a colligative property is the lowering of the freezing point of water by a solute such as salt. A salt water solution has a lower freezing point and a higher boiling point than pure water. The lowering of the freezing point is the reason that salt is applied to icy roads in the winter. The salt lowers the freezing point of water and therefore helps to melt the ice at lower temperatures. Let's examine several colligative properties. The first one is vapor pressure lowering. The vapor pressure of a solution is lower than the vapor pressure of the pure solvent. The vapor pressure is lower according to Raoult's law, which states that the vapor pressure of a solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. So for example, if you have an aqueous solution that is 90% water and 10% solute particles, then the vapor pressure of the solution is 90% of the vapor pressure of the pure solvent. As we just discussed, other colligative properties include freezing point depression and boiling point elevation. The freezing point of a solution is lower than that of the pure solvent, and the boiling point is higher. Both of these properties are a direct result of vapor pressure lowering. Let's look at the phase diagram for a pure substance. As we just saw, a solution has a lower vapor pressure than its pure solvent, so the vapor pressure curve is lower on the phase diagram. Therefore, the fusion curve must move to the left. That's in order for both of the curves to meet at the triple point. The result is that the freezing point is lowered and the boiling point is raised. The equations that quantify freezing point depression and boiling point elevation are similar in form. For freezing point depression, the lowering of the freezing point, delta Tf, is equal to the molality of the solution times the freezing point depression constant for the solvent. For water, Kf equals 1.86 degrees Celsius over molal. For boiling point elevation, the elevation of the boiling point, delta Tb, is equal to the molality of the solution times the boiling point elevation constant for the solvent. For water, Kb equals 0.512 degrees Celsius over molal. For example, a 1 molal aqueous solution has delta Tf of 1.86, which means it has a freezing point of negative 1.86 degrees Celsius. The same solution has a delta Tb of 0.512 degrees Celsius, and therefore a boiling point of 100.512 degrees Celsius. The final colligative property that we cover here is osmotic pressure, the pressure required to stop osmotic flow. Osmotic flow is the flow of a solvent from a solution of lower solute concentration to one of higher solute concentration. Osmotic flow occurs in an osmosis cell, such as the one shown here. The left side of this cell contains an aqueous solution, and the right side contains pure water. The solution draws pure water to itself through the semipermeable membrane, and the level on the left side of the cell rises while the level on the right side of the cell falls. The flow will continue until the weight of the column of solution on the left equals the osmotic pressure of the solution, which depends on the concentration of the solution. The equation that describes this behavior is pi is equal to mRT, where pi is the osmotic pressure, m is the molarity of the solution, and r is the ideal gas constant. One last word about colligative properties. A strong electrolyte solution produces more of an effect on colligative properties than a non-electrolyte solution of the same molar concentration. This is because strong electrolytes dissociate in solution to produce a greater number of dissolved particles. For example, a 1 molar sodium chloride solution contains nearly twice the concentration of the dissolved particles. This is because each NaCl unit produces 2 dissolved particles in solution. So, if 4 formula units of sodium chloride dissolve, then 8 particles result in solution. The equations for colligative properties must therefore be modified for strong electrolytes, as shown here for freezing point depression, boiling point elevation, and osmotic pressure. The I in each of these equations is the ratio of moles of particles in solution divided by the moles of formula units that dissolve. For example, for sodium chloride, we would expect I to be 2. It is actually a little bit less than 2 for reasons that you can explore in your book. Which solution has the highest boiling point? A, 1 molar C6H12O6, B, 1 molar KCl, or C, 1 molar MgNO3-2.
All right, so which solution would have the highest boiling point? And hopefully you would say, just based on watching that video, magnesium nitrate, right? Because it's going to break up into more ions. But we'll discuss that more in the next few videos together. So hopefully you get a really nice visual there of what's going on. Let's now kind of review over what was said and then focus on vapor pressure. All right, so colligative properties depend on the number of particles. It doesn't matter the type of particle, right? It just depends on the number of particles dissolved in the solution. So for example, if you have sucrose, which is an organic molecule, it's not going to break up into ions, right? Versus something like sodium chloride, which breaks up into 2 ions, sodium +1 and chloride -1, right? You're going to have more particles dissolving sodium chloride versus sucrose, which is covalent, okay? So the vapor pressure lowering, as was said in the video, the trend is the vapor pressure of the solution is lower than the vapor pressure of the solvent. Why is that? Well, let's think about what we've been discussing in previous videos. Nature has a tendency towards mixing. And we discussed that when we investigated enthalpy of solution based on the enthalpy of the solute and the solvent and the enthalpy of mixing. And nature also has a tendency towards entropy. It wants more disorder. And so that was all based on the second law of thermodynamics, that the entropy of the universe is always increasing for spontaneous processes. And so basically what is happening is when you add these particles, they're mixing. They don't want to go from a liquid to a gas. So that lowers that vapor pressure of the original solvent because they're too busy mixing with one another rather than going into the gas phase and bumping into sides of a sealed container, right? And we can quantify that, the vapor pressure of the solution, using Raoult's law. So the vapor pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the solvent. And anytime you see the degree symbol here, that means that was a literature value you can look up, and usually done in standard conditions. And that's 1 atmosphere, 25 degrees Celsius. In terms of like standard conditions, 1 molarity. So it depends on what literature constant we're looking up here. But yeah, that degree symbol just means you're working under standard conditions. And so this is definitely the vapor pressure of a solvent at 25 degrees Celsius. Okay? And we discussed in the previous video how to calculate mole fractions. I want to make note that it's the mole fraction of the solvent and not of the solute. And then we'll see how that affects the vapor pressure of the solution. So let's work an example together. We have a solution that contains naphthalene, and it's dissolved in hexane. And so that tells you that naphthalene is your solute. And that hexane is your solvent. And it's important that we identify this when we're calculating concentrations. And we are given that it is 12.35% by mass of naphthalene in hexane. And we are asked to calculate the vapor pressure of the solution. And they give us the vapor pressure of the solvent, which is hexane, at 25 degrees Celsius equal to 151 torr. And we're trying to find the vapor pressure of the solution after we add the naphthalene. We know that we can find the vapor pressure of the solution using Raoult's laws. I'm going to write that equation down again. So the vapor pressure of the solution is equal to the mole fraction of the solvent, and we've identified that to be hexane, times the vapor pressure of that solvent which is given to us, or we could look that up in literature, and that was 151 torr. And so our goal here is to find the mole fraction of the solvent before we can find the vapor pressure of the solution. Okay. And we're given a concentration of 12.35% by mass. And what I always tell students, when you have mass percent, assume you have 100 grams of solution. And if you have 100 grams of solution, then how many grams of naphthalene do you have based on the given piece of information? Excellent. You would have 12.35 grams of naphthalene in a 100 gram solution based on this mass percent. So you don't have to assume you have 100 grams of solution. I just always feel like it makes the math a little bit easier. And so let's go ahead and I will write down the formula C10H8 for naphthalene. Hexane is C6H14. We'll need that for the molar mass. And so right now we're talking about naphthalene, and that has we want to convert that into moles, and that has a molar mass of 128.16 grams. And therefore we have 0.096363 moles of naphthalene, which is our solute. We also have to figure out the moles of the solvent, right? Because we can't just figure out moles of solution because there's two different things in there. So we have to figure out the moles of the solvent. And remember that the solution is always composed of your solute plus your solvent. And so we know we assumed we have 100 grams of solution. We know we have 12.35 grams of naphthalene. So if we take 100 minus 12.35, we can figure out the grams of hexane in our solution. Which is 87.65 grams of hexane. We want to convert that into moles. Hexane has a molar mass of 86.18 grams. And you get 1.017057 moles of hexane, C6H14. All right, I'm going to highlight some pieces of information that we will need. So we'll have to calculate the mole fraction of hexane. And remember, when you do mole fraction from the previous video, it's always the part over the whole. So we need moles of the hexane over the total moles of solution. Over the total moles of solution, which is the moles of the solvent, plus the moles of the solute, which is 0.096363 moles. That's the total moles of solution. When you plug that into your calculator, you should get 0.913453. And this is unitless because it's always moles over moles. So when you're doing a fraction, it should be unitless. And then now we have the mole fraction of hexane, and we have the vapor pressure of pure hexane. So now we can plug and check and calculate the vapor pressure of the solution after the naphthalene has been added using Raoult's law. So vapor pressure of the solution is equal to the mole fraction of the hexane in our solution. Remember, use mole fraction of the solvent, not the solute. And then times 151 torr, which is the vapor pressure of pure hexane. And when we plug that into our calculator, we should get 137.93 torr, which is the vapor pressure of the solution, rounded to 3 significant figures because 151 torr is a measurement. So that's the fewest sig figs we have here. So the vapor pressure of our solution, our final answer, is 138 torr. And I always tell students, when you solve a word problem, you want to rationalize it. You want to make sure that you're confident in your final answer. And so ask yourself, does this final answer make sense given the context of the problem? We just learned that the structure-property relationship and the relationship between vapor pressure of a solution versus vapor pressure of a solvent is that it should be lower, and that's really important to remember. So when you do this calculation here, you learn that the vapor pressure of the solvent is 151 torr. Therefore, when calculating the vapor pressure of the solution, your final answer should be lower than the vapor pressure of hexane. If you get an answer higher than the vapor pressure of hexane, then maybe you have an algebra error or a calculator error. So whenever you're working any problem, always ask yourself, does this make sense based on the theory that I understand and also structure-property relationships? Thank you all for watching, and see you next time.